Thanks for the introduction. This work is also, so I'm doing this work with a fantastic supervising team, so also thanks to them. And I'm from Johannes Kepler University in Linz in Austria, and this work is also done in cooperation with Oracle Labs. So one of the first questions when attending this talk is, why should we care about hybrid execution, and which kinds of executions are here merged? So imagine you have your source code. A typical way is to compile it to machine code. This is done ahead of time, so it's compile time, and then at runtime we run this code. So this is commonly known as ahead of time compilation, where you see that the optimization is done at compile time, and then the code is run at runtime. However, there is also a second way of executing programs, which is to use an interpreter. And when we analyze the code into an interpreter and profile it, we can also optimize it and produce machine code just in time. Therefore, this is called just-in-time compilation. And here, execution or interpretation and optimization influence each other. And we want to combine these two approaches for the same source code, because for ahead-of-time compilation, you have the nice property that there is no warm-up costs, but for JIT compilation, you can achieve a very high peak performance. And this is the reason we want to combine it to get the best of both. And we implemented our approach on GraalVM and for C code as an example. And how this is done is, there is GraalVM offers the LLVM runtime Zulong, and if you use Clang, for example, or Clang, then ahead of time, this compiler generates LLVMIR and then also emits binary machine code. And this can be shipped in one file. And if Zulong receives such a file, it then creates an abstract syntax tree out of the LLVMIR, and this abstract syntax tree is then forwarded to the JIT compiler. However, there is also the opportunity to use the native function interface of GraalVM, which offers to directly execute the binary machine code on the native side, on the CPU. And this is our hybrid execution model. So we have native execution, where compilation happens ahead of time, and we have managed execution as well. And those who attended VMIL last year might remember a similar slide, because there we presented the basic approach where the decision how to execute the functions are taken by the developer. So the developer had to annotate the functions, more or less. This was more a proof of concept that hybrid execution is useful. And now we want to get a step further. But first, some technical basis. So we have source code, and in this example, we have 3 functions that are calling each other. And the abstract syntax tree looks, if it's a bit simplified, looks like this. Then machine code looks like this. And let's say now we want to run B in the native mode and C in the managed mode. The way how we had to change execution is to forward the calls to B, for example, to the native side. And if we want to execute C on the managed side, we also have to forward the call from the native side to the managed AST node. And the modifications on the native side were not there last year. So this is an extension we had to do for the automated approach, and they're also platform dependent. But our goal now is to extend this and to do an automated decision. On the one hand, the programmer doesn't know the whole program code, and also doesn't have to have the deepest compiler knowledge, so to say, if this decision is automated. And for this, we start the execution by managed execution only in a profiling run. There we can track the program and create a call graph with necessary information. And then we apply some calculations. We write everything into a specification file, which is stored. And if there is a follow-up run, we can then use this information, and then the functions are run natively if our heuristics decided to do so. And talking about the applying heuristics already, this is the major part of the presentation now, because this was also the major work. It was not that we directly came up with this, but it was an iterative process and still ongoing process. So the journey has not ended yet, but this is the current state. So the general problem is that we have a function f, and we have to decide, do we want to execute this on the managed side, or should we go for native execution? And the current way is shown here, actually a little bit past, because the paper deadline is also already some months ago. And I will just explain those 3 steps in detail now. So the first question is if the function accesses managed data. And this is important because GraalVM is a polyglot execution machine. So when we execute C code there, and also source code of other functions, it can be that the C code accesses code of other functions. For example, today we had a lot of Python talks already, and also C extensions, native extensions we already mentioned. This is a classical example that you have some Python code and some C code, and of course those 2 languages, or code of those 2 languages, will interfere with each other. And let's start with a simple function add_point that adds a point to a global data structure. And if we assume that everything is on the managed side, we have a function add_point and also a point list, so to say, called data m, or data managed here. Then the function accesses the data structure. This can also happen on the native side, and this is also possible if we have a managed function, that the managed function accesses the native data. However, in the other direction, we have a problem. The details are listed in the paper. The simplified major reason is that we have to guarantee the semantic correctness. And we cannot, for example, store a JavaScript object correctly in C, but we have to use the JavaScript runtime for this. And therefore, this has to be managed. But it can be, so we have 2 different cases. In the easy case, for example, when it is a managed C struct, it can be easily converted to the native side, because also the C code can be compiled to the native side. Then it's no problem to access the data from both versions. However, in another scenario, which I will show on the next slide, it can be that the managed data cannot be converted to native representation. And then we have to execute the method that accesses this data also on the managed side. So as an example, we could have C code here. As shown, we have the add_point function. And if the data points to an array, then it could be that the first 2 points, for example, are C points. If this is on the managed side, it can be moved to the native side without problems. But if we have a Python point, for example, then we have to access this add_point method on the managed side. Important to mention here, if we only access the element 0 and 1 of this array, the function can still be executed on the native side. So it's really when we access the data element itself. So this is the reason, if we access managed data, then we have to go for managed execution. The second point in our heuristics is to take a look at the static function size. And because we want to achieve a fast decision, of course we could analyze the whole call tree here and would get an optimal result, but we don't consider this as possible because we have to get fast to a relatively good decision. And for this, we took a look at the function size, and it's not 100% correct what is shown here with the small text. Therefore, we will take a look in detail. So we wrote several C functions with different sizes without control flow. So this is important that I mentioned this here, and tracked the performance. And it was nice to see that we have linear dependency here. And from this point of view, it's clear if a function is larger than 30 kilobytes of LLVM bitcode, then we execute this on the native side, otherwise on the managed side. However, the no control flow is a bit tricky because you can relatively simply come up with an example where static code size and the amount of executed instructions contradict each other. So here, for example, we have a simple loop with 1,000 iterations. And there you can see that the second example, which has the larger static code size, has less executed instructions in total. And as said, we don't have to go for a perfect solution here because it's just heuristics. But we here just assume that every loop level increases the function size by 10. So we go for the maximum level of nested loops and multiply. We actually, for every nested loop from the maximum size, maximum level of nested loop, we multiply this by 10. We also try different numbers, of course. It's not that we just pick 10, but 10 lead to the best result. And the number of static loops can be also relatively fast determined. So in this example, we have the code on the left side, which contains 3 loops actually, and 1 branch, but now we only care about the maximum loop level. And LLVM is structured in as a control flow graph, so we have basic blocks, and we just count back edges. So for the while loop, the graph looks as follows. For the outer one, then we have a while loop in between, which is just 1 basic block, and then we have another different basic blocks, which also describe the green while function here in the middle. And what we do here is we just enter the basic blocks with an back edge, so either it's in or outgoing. We put them in a sorted list, and then if it's an ingoing edge, we know that the loop level will increase. If it's an outgoing edge, we know that the loop level will decrease. So we just iterate at the end over this table, and then can determine the maximum number of loops. So this was the second criteria. And then we have still some functions. So only the large functions are set for native execution, and the smaller functions are still not determined. And for these functions, we take a look at the call overhead. So when a native function calls a native function, or a managed function calls a managed function, the 2 top cases here, you see that there is roughly no call overhead. However, when we change the execution mode, of course, also there are settings in the runtime that have to be set, for example, and especially when you do a so-called up call, so when there is a native function calling a managed function, we have a very high overhead here, which cannot be neglected. So imagine you have a lot of small functions. For example, our most call functions are actually in the benchmark then the increment reference and decrement reference methods of Python, for example, in C. Imagine you do a chain of small function calls. If they always switch back and forth between the modes, you have a lot of call overhead. And therefore, we use the call graph information which we have. So starting from a function f, we have a managed and a native caller, and also the call frequencies. We also have the call frequencies of the callees, so the function that f is calling, and then we just assume both sides. So first, we assume managed execution. There we know that we can ignore the managed caller and the managed callee. But for the native caller, we know that we have up call costs. For the native callees, we know that we have down call costs. And then we just put this together in a simple formula. This looks a little bit more complicated, but it's not very complicated at all. It's just calculating the time. And here there are 2 variables, in u and out u, which I have not explained yet. So this is the number of undetermined functions yet, because we still have functions where we don't know how we want to execute them. And for them, we just assume that half of them will be managed and half of them will be native. And this is where these terms come from. And then we do the same for native execution. So we know that we have down calls from managed callers. And if a native function is calling managed callee, this is an up call. And similar, we use the formula for this situation, and then we do a simple comparison. And with this, our simple heuristics, or our fast heuristics, is finished. So for an example, we use a Python application, for example, that has a C extension, and now we take a look at the C extension. So first, we check if the function accesses managed data. And this is the case, because the function f in this case accesses the Python data var. Therefore, f has to go for managed execution. Then we can check the size of functions. And the function C is a large function here. Therefore, it's we mark C for native execution. And then we do the call overhead calculation, and I haven't drawn the call frequencies here, but we just assume that this is the result in this case. Since the time elapsed between paper submission and now, for example, what we also tried is if e is a very small function, we duplicate the function or we run it in both modes, but the results are preliminary and not really fixed yet, and we also would like to discover the results. But what we did is if e is called from B, then it's executed on the managed side. If e is called from C, then it's executed on the native side, if e is a very small function. This is also something we tried in the meantime, but this is not written in the paper yet, of course. Yeah, so with our final result, let's take a look at some benchmarks. Of course, we didn't try just the Python benchmark suite that is available, because our work has been done for C and for native extensions. So we ran Python programs with native extensions, and we always tried them in 3 different modes. So the first mode to compare is fully managed execution. So every function is executed in the managed side. The other thing we tried is native execution for most functions. This means all functions that have to be managed run managed because they access managed data. But for every other function, we leave it for native execution. And then we have our hybrid mode with the proposed heuristics you saw on the last slide. And I picked up 2 benchmarks where to show interesting behavior, so to say. The first one is the LXML benchmark suite. So here, XML data is parsed, and there is work performed on it. There are 20 different tasks. What we measured is the time it took for the data to be loaded. So this is the left column here. And then out of the different tasks, they can be grouped into annotation tasks and path tasks, path finding tasks. So we group them by the general task, so to say, to see the interesting behavior. And what can be seen for warm-up performance is that native execution is always performing best. This is no surprise. This is what we expected, because if more code is executed on the native side, of course, there's also less analysis by the profiler for cheat compilation necessary. And then we have, for peak performance, we have 2 different results. The one is for annotation tasks. We can even, with the hybrid mode, even outpass the other 2 versions. So here, the hybrid mode really pays off. On the other hand, there is also code where the hybrid mode performs less than fully managed execution. And this is, for example, because the GraalVM cheat compiler can then aggressively optimize this a very complex system, a very complex compiler. There's inlining involved, and if we move certain functions to the native side, of course, the GraalVM cheat compiler cannot inline these functions anymore. And this is just one example why fully managed execution is sometimes a better choice. And also in the follow-up work, we would like to improve our prediction skills, so to say. So if we get some piece of code, we would like to predict in a better way as we can do now which mode should be chosen. And the other benchmark I would like to show is the JSON benchmark. So when we go back, this is kind of the same situation we had for the annotation tasks for the middle column here. What is done there? JSON data is loaded and parsed and then dumped again. And what can be seen here? So on the one hand, for loading the data, the native mode is the better choice. However, for dumping the data, the managed mode is the better choice, which is the bar at the bottom. And our hybrid mode is always in between those 2. However, if we take a look at the total time, our hybrid mode is faster than the accumulated times of both modes on the side, so to say. And this is an example where the hybrid mode finds a sweet spot. And this is also why, for example, the annotating task before can achieve a speedup, because we find a middle way of two different modes. However, as already said, we would like to also investigate a little bit more and being able to predict in a better way which execution should be taken. And what's also interesting is if we have, because currently the decision how a function is executed is taken at the beginning when the program is loaded. However, we would like to also do this at runtime because, for example, we can start more on the native side, and then if we realize that maybe switching to managed execution is useful, we can switch to managed execution to enable high peak performance, but we still got a good warm-up performance due to the native execution in the beginning. So to wrap everything up, we proposed hybrid execution in the beginning with an automated approach this time, such that there is no work left for the programmer. We came up with a fast heuristics. I'm sure this is not the best heuristics you can come up with, but we needed an approach which evaluates fast. And then we also saw that it does not always perform in the best way, but there are situations where our hybrid mode is definitely a thing for a good choice. And with this, I would like to thank you for your attention and hand over to the discussion part. Thank you.
We've got time for about 2, 3, or 4 questions, I think. Yes, go ahead.
Hi, interesting topic. One thing that bothers me with in such a setup is the overhead that one has to pay to identify if the AOT code is valid or not. Because you have some AOT code which is already stored, and now the bytecode has changed, the class files have changed, right? So now all those checks will be added to this series of steps, isn't it?
The thing is that in our system, let's check it. Maybe there is even a faster choice for this. Yes. That when we restart the process, in this case, we still, even the just-in-time compilation starts from scratch again. So we really start with a correct program state again, because at program initialization, we say that that some functions are executed on the native side, and some functions are executed on the managed side. And then the program, of course, the GraalVM cheat compiler can now not look into the native code, and therefore it just assumes that the native code is correct itself, but it does not reuse.
No, I guess here's the deal, right? I mean, the JIT code has been, while the Java, the JVM is running, the JIT code is generated, all right? And in that, there is a call to an AOT method.
Yes, but profiling restarts from scratch again in the next run.
In the same run, see, it's a long-running program.
Yes.
In the long-running program, there is a call to an AOT method.
Yes, but there we invalidate the things the JIT compiler did. So we restart from scratch when we use the decision.
Okay, yeah.
Of course, there is also, I think the last talk or one of the next talks is to reuse JIT compiled code. This is another approach. We really go for the ahead of time compiled code in this case.
Yeah, I might miss Ari part of the presentation, but let me clarify the motivation. So I think the target code, source code, is in the C language. Is that right?
Yes.
So I wonder, well, because the C language is pretty static. So I wonder, why you have to, do AOT compilation for the C code.
So I'm not sure if I got the question. The question is why we also use JIT compilation for C code if it can be.
Yeah, okay. To me, because the source code is a C.
Yes.
So doing the AOT compilation would be quite straightforward, and in a certain sense, you can do AOT for every C source.
That's true, yeah. Of course,
why you have to switch?
If you have C code only, then AOT compilation might and probably will be the better choice. But we also have in GraalVM the situation that you can mix programming languages. And especially when you mix programming languages, it can happen that you have to access, for example, Python code from C. And if this point is stored in a C array, but it is a Python point, if you use GraalVM and execute this code, then automatically the Python runtime is invoked when we access Python data. So if it's C code only, then of course AOT compilation would be the better choice. But since we also have different languages that interact with each other, it sometimes is necessary to go back to the managed side.
Thank you.
Yeah.
Thank you for your talk. If I got it correctly, when you want to determine whether a function should be executed in native mode, you look at the at whether the callee and the color are native or managed. And would it make sense to go a bit further in the graph, in the call graph, and to look at the nodes that are the color of the color or the callee of the callee? Because if I got it correctly, there is some cost associated to context switch. So would it make sense?
Definitely. The thing is, I haven't tested it for speed because we need a fast decision. If we apply an NP-complete algorithm for this, it might take very long. And if we can run the application before, and it doesn't matter how long it runs before, because we do the profiling run, and then at a later point in time we want a fast execution, then this would be a very valid choice. However, I haven't tried, I have to admit I haven't tried graph coloring algorithms for this situation yet, because we want we want this process to happen fast. But definitely a good point, especially when we have the time in a situation to try this, because then we could also go for an optimal solution, I think, instead of just guessing which way would be the fastest.
Thank you.
Right. Okay. So my concern here is that you use some magic numbers in your heuristic there. There's a 10 for the code bloat size based on loops, right?
Yes.
And there's a 2 based on the fact that you arbitrarily split them 50-50. How many programs / benchmarks did you use to actually come up with those numbers?
For 10, we used the benchmarks presented here, because with those we could also achieve speedups. And for the 2, we actually also checked for, it was not exactly half, it was a bit more on the managed side. So it would be not divided by 2 and multiplied by 0.5, it would be multiplied by 0.56 or so. Again, this is also because we just needed to get to a fast result. But that's true, we could also adjust this. If we see that in a benchmark, for example, in the LXML benchmark, we use, I think, only a third or even less, 22%. Yes, here in this case, only 22% of the functions are native. Then we could also adjust this divided by 2 to make it more appropriate to the actual situation in the application. But we don't know this beforehand.
Right. So, but you do need to adjust based on benchmark then.
Yes, so we just saw that for the given benchmarks, this works well. We also tried it with different parameters instead of dividing by 2 with multiplying by 0.6 and other numbers. The reason why we stayed with 0.2 is it got the best results for the benchmarks we tried here. But of course, in this case, if we only have 22%, then the division by 2 is not the right choice, obviously. But we don't know beforehand how much functions will be on the native side. This is why we go with the not really precise version.